Okay, we are ready to start. Welcome everyone, and thanks for joining us today for Neuroelectrics webinar. My name is Rafał Nowak, and I will be again your host today. So this is the 11th of a series of Neuroelectrics webinars, and now we have already more than 100 participants, so we are very happy with this. Today we'll be talking about the mechanism and advanced applications of transcranial alternating current stimulation. I'm very happy to welcome our guest speaker, Dr. Ivan Alekseichuk. Good morning, Ivan.
Good morning, Rafał, and good morning, everyone. Great to see such good attendance.
Good to have you here, Ivan. Before we get started, some additional information. We'll begin with Ivan's presentation. This will be followed by Q&A period. So please free to submit your questions at any time using the Q&A tool. The recorded version of this webinar will be also available offline. So please let me quickly introduce our speaker, Dr. Ivan Alekseichuk. Ivan is a researcher in the Department of Biomedical Engineering at the University of Minnesota Twin Cities in the US. He investigates the physiology and biophysics of transcranial brain stimulation methods in animals, models, and in humans. And he coordinates clinical trials involving the model-driven transcranial alternating current stimulation. His goal is to advance our understanding of cognitive processes and to create ways to augment them with neuromodulation. So I'm happy as we have a lot of shared interest with us here at Neuroelectrics. Let me add that Ivan did his PhD studies in systems neuroscience in the group of Professor Walter Paulus at the University of Göttingen in Germany. And actually, we are mentioning Göttingen. I know even since many years, thanks to practical transcranial electrical stimulation courses organized every year in Göttingen. So this is actually a great opportunity to send our warm regards to the whole brain stimulation group in Göttingen. Professor Walter Paulus, Professor Andrea Antal, and also former labs members, Agida, Alex, Zolt, Gabriel, and all senior researchers and postdocs who are nowadays doing research across the globe, and obviously including Ivan in Minnesota. So welcome, Ivan. The stage is yours.
Thank you, Rafał, for introduction. And of course, I also would like to join and send my regards to University of Göttingen, where I spent 4 very productive years. And now let's start with the presentation. So I hope you can see my screen. And so I will talk today about the mechanisms and advanced applications of transcranial alternating current stimulation. And first, declaration of conflict of interest or no conflict of interest, because I have none. And my research currently is supported by University of Minnesota MinDrive Initiative and National Institute of Health Brain Initiative. So, transcranial alternating current stimulation, as we all know, is a method of non-invasive neuromodulation via application of weak time-varying electric currents through the scalp. And in typical application, we are using electric currents somewhere around 1 or 2 milliamp, so very safe in our dose, and anywhere between single channel and multi-channel applications, with a typical session lasting somewhere between 5 and 20 minutes, maybe 5 and 30 minutes. And of course, one of the main strengths of this method is that it is non-invasive, so allow for safe application and wider range of applications in humans. But with that, when it comes to the research, its non-invasiveness also have a double edge, which means that we cannot really know what's happening inside of the brain during the stimulation unless we observe what's happening in the brain during the stimulation using some invasive methods. And it's very important for us to know exactly the mechanisms of what's happening in the brain during applications. And here animal studies, of course, can help us out. And in our recent study that we published in a group of Alekseichuk here in the University of Minnesota, we recorded single unit activity invasively in the neocortex of awake non-human primates, in awake monkeys, while we stimulated at different intensities using classical tACS or transcranial alternate current stimulation approach. In this classical approach, you would have two electrodes non-invasively positioned on the skin, and we apply alternate current at different intensities, and here it was frequency of 10 Hz, while we recorded invasively at single units from the surface of from the neocortex in monkeys. And advantage of having invasive recording is not only in signal to noise ratio, but also in the fact that neural spikes, although it's also electrical activity, they happen in a very different frequency range and has very different domain rather than continuous slow electrical current at 10 Hz that we apply. Therefore, although there are many troubles you can run into if you will try record, let's say, EEG or MAG during tACS, although some groups try to do that, while you have when you record single units activity, it's really not a problem. And here I have a snippet of the raw data recorded during the stimulation. So because we apply electrical current, obviously you have a large artifact during the stimulation that captures our stimulation components. But anyway, you still can clearly see the spiking activity. So here I colored them in orange, and then you can simply filter out the data and extract the spikes. And with that, you can then analyze the spikes with respect to the phase of applied alternating current in order to explore what happens with the spike timing, with spike rate and alignment of spikes to applied alternating current. And we did this at 3 different intensities in order to look at the dose dependency. And because we have invasive recordings, we also can estimate electric field in the brain. It's actually not a modeling result, this is estimation result, so we have measurement results, so we have them only in the area of recordings. And at 3 different intensities, we estimated about maybe 1.5 volt per meter per applied milliamp, which is roughly, which means that 0.5 milliamp to 1 milliamp is approximately electric field that you can achieve in humans in actual practice. So we analyzed spike timing with respect to the applied alternating current to see if there are effects on spike entrainment. And we identify that during the stimulation with 0.5 milliamp, 1 and 1.5 milliamp, there is like 9, 18, 27% of all observed neurons that were statistically significantly entrained by applied alternating current. And here there is one of these neurons represented on the screen. So in 3 columns, we have 3 different intensities. And for each intensity, spike timing was cut on periods of 200 milliseconds that align to the applied alternating current. So here you can see the waveform of applied alternating current, and each dot represents a single spike. And first period in black color, we have pre-stimulation period, then we stimulate for 2 minutes, and then we have post-stimulation period. And you can clearly see that in the pre and post-stimulation period, the neuron exhibit random spikes relative to the like propagated or fitted phase of alternating current, if you just continue it. However, during the stimulation, spikes are clearly organized in a periods of preferential spiking during the peaks of applied current, and there is suppression during the troughs of applied current, and this is dose dependent. And at the bottom you can see periodogram, so just a sum for spike timing over time. And as I mentioned, this is just one neuron, but we can look on all of them, or at least on one another neuron that exhibit very different patterns of spiking. Here in the bottom row, another representative neuron, very high spiking. However, there are still all effects present, and as far as we can see from the data, what happens with the neurons during the application of transcranial alternating current stimulation is spike entrainment. So there are spikes preferentially spike at a peak of current and suppressed at the trough. And if you think about how brain communicates and what spike timing actually mean for the brain, so about the rule of plasticity, you then can deduct what would be the main mechanisms of actions for transcranial alternating current stimulation, for tACS, which is most likely at the first stage as a spike entrainment, and then manipulation with plasticity, because we know that neurons that are spiking together are wired together, right, by the Hebbian rules. And yes, so this mechanism already was postulated before our study for a long time. However, here in awake primates, we demonstrate that it's possible to achieve it in a dose range that is reasonable and achievable in humans. This is a summary statistic. We can take a look on phase lock-in value, which is a measure of phase entrainment to the applied current for all recorded neurons and for those neurons that eventually responded to the stimulation. We can see that there are subpopulations of neurons that respond to stimulation. As I mentioned, it's about quarter to 1/3, which probably relates both to the physiology of neurons that we're recording, so what kind of neurons are they, and alignment of neurons to the electric field, because we have one particular montage, which means that some neurons are better aligned to the electric field than the others. Besides, we also take a look on the spike rate, so then the frequency of on the total frequency of spiking during stimulation relative to pre and post stimulation, and we found no changes. There's no statistically significant changes in spike rate at either intensity and in subpopulation of responsive neuron or in any other neurons that we have recorded. So changes in spike rate, at least during ongoing stimulation, seems not to be the mechanisms. In order to demonstrate that this is a brain-specific effect rather than effect driven by cutaneous stimulation, because we also obviously stimulate skin, peripheral nervous system, we had a cutaneous stimulation control at 1 milliamp, where we apply stimulation not to the brain but to neck and shoulder of non-human primates, and we demonstrate that there was literally no neurons that react in any way during the cutaneous stimulation of 1 milliamp. So there was no changes in spike rate and no changes in phase lock-in value. So there was no entrainment to the applied alternating current during the cutaneous stimulation. As I mentioned, we can estimate the electric field in the area of recordings and see if there is dependence from between the electric field achieved in the brain and phase lock-in value, so degree of entrainment during the stimulation relative to pre and post stimulation period. And again, we see basically two subpopulations of neurons. Each neuron on this graph is depicted with one pictogram depending on the intensity of the stimulation, and there is subpopulations of neuron that is clearly that's clearly demonstrated those dependent effects of entrainment, which are close to linear. And then there are other population of neuron that doesn't respond. It's also interesting to see that most of the neurons that, or actually all neurons that have responded, they actually responded in the at the electric field somewhere between 0.3 and 1.3 millivolt per millimeter, which is reported in the literature as values that are in principle achievable in humans, especially values like 0.5 to 0.8 volt per meter is a range where is a range readily achievable in human applications, and we demonstrate that there is a population of neuron that is significantly entrained at these intensities. However, besides entrainment, we saw another mechanisms, and first I would like to take a look at the entrainment on a different angle. So this is peristimulus histogram, histograms during the stimulations. Again, stimulation at half a milliamp, 1 milliamp, 1.5 milliamp in different columns, and in the rows we see the stimulation during rest, pre and post, or we see periodogram during rest, so pre and post periods, and then during the stimulation, and then the difference. And because we stimulated at 100, at 10 hertz, which has a period of 100 milliseconds, what happens with neurons during the stimulation is that spiking kind of mostly happens at the peaks of 100 millisecond waveform. So the color on this periodogram encodes probability of spiking, and x-axis and y there are like spike at time point n, and y-axis spike at time spike at time point n+1. So what is the time in between one spike and another spike? And we can see that when there is a stimulation, there is a high chance that after the first spike, the next will come in 100 milliseconds, which correspond to the entrainment to 10 hertz. So this is a picture that we saw in one subpopulation of neurons, but then there was another where we also saw statistically significant effects of tACS, but of different kinds. Here, again, on the top row is rest, and then there is stimulation, and there is difference. And what we see here is that there was a subpopulation of neurons that demonstrate increase in burstiness. In other words, whenever this neuron spike, there is very high probability that it will immediately follow up with another spike. So spikes kind of clustered in this neuron, so they come in burst. However, the total amount of spike per the whole stimulation period, let's say it was 2 minutes in our case, have not changed. So while the spike rate and total amount of spike didn't change, spikes now in the subpopulation of neurons, spikes now were arriving in a burst, so a much higher clustering. Overall, we demonstrate in this study direct and dose-dependent cellular level effects of transcranial alternating current stimulation in awake primate brain. We demonstrate that at intensities readily achievable in humans at half to 1 volt per meter, we see statistically significant phase entrainment. And besides, there may be more to this story, so there may be other mechanisms involved that we set to explore, and hopefully I will be able to report them rather soon. Here I also want to highlight another recent study by our colleagues, so Matt Crozier and Christopher Park from Canada. Also take a look on transcranial alternating current stimulation in single neuron activity in primate brain. in awake primate brain. However, they set to explore frequency specificity of stimulation rather than dose specificity, and I think these results complement very nicely to what we observe and agree with them. In their research, they applied stimulation at single intensity, I think it was 2 milliamp, while they stimulated 5 Hertz, 10 Hertz, 20 Hertz, and 40 Hertz. And they also take a look on spike rate and degree of entrainment to the phase of alternating current. And in these types of histograms, you see the values during the sham on x-axis and values during tACS on y-axis, and whatever is each neuron that lie on a diagonal pretty much has no changes between sham and tACS, and neurons that have deviation from diagonal have statistically significant changes, and such neurons are depicted in red. And we can see that our colleagues also observe almost no changes in spike rate, in total amount of spikes per stimulation period at either stimulation frequency. However, they observed statistically significant entrainment and phase lock-in value, and this entrainment was frequency specific. So while applied stimulation 5 Hz, they mostly saw entrainment at around 5 Hz, but never else in the analyzed spectrum, and they analyzed between 1 and 100 Hz. And same for 10 Hz, 20 Hz, and 40 Hz. So it was demonstrated that the entrainment is indeed frequency specific, and there is slight difference in population of neurons that responded depending on frequency. So not all neurons responded to all stimulation frequencies, but some responded to multiple. So it's slightly more complicated story than a classical idea of Arnold's tongue. Nevertheless, it's largely agreed with that. So applied stimulation actually entrain neuron at the frequency of the stimulation. That gives us good understanding of the standard mechanisms of tACS and how they act, at least in primate brain, which arm us with knowledge necessary in order to apply it in humans. However, moving to human application, it's also very important to have clear understanding of what is the difference between different laboratory animals and human, and what happens in the brain depending on how electric current differently maybe affect brain of different laboratory species, and how to translate stimulation parameters between rodents, where a lot of earlier research with electric current were made, and monkeys and humans. And we recently were set to explore this using computational modeling. In our recent study, we modeled mouse brain, capuchin and macaque monkey's brain, and human brain using finite element method modeling approach. In this approach, you first obtain individual imaging. So it was CT scans or MRI scans of a mouse. In our case, we used the imaging of a Digi mouse, which is a popular atlas for mouse, of a monkey and a human, and these images then can be segmented on soft tissues, bones, CSF, gray-white matter. These tissues then can form boundaries for our computational modeling. And here at the lower row you can see a slice through our modeling, and you can see tissues organized there. So mouse, monkey, and human is species of very different sizes, as we all know, but that's not the only part of the story. So we wanted to look how electric current stimulation will differentially affect such different brains, and we set to explore 3 different electrode montage, which was a left-right temporal electrode montage, anterior-posterior electrode montage, and dorsal ventral, so stimulation of M1. And we applied the stimulation at the same intensity here, and it was 1 milliamp. And we recorded what kind of and we estimated or simulated what kind of electric field we will see in the brain. This value can be flipped. So knowing, so if you say if we know that for 1 milliamp we see at about 20 volt per meter in the mouse, but let's say only 0.4 volt per meter in human, we can recalculate what intensity we need in order to achieve comparable electric fields in this species. And that's actually what we saw. This is one of the montages, left-right electrode montage. We saw that there is a difference in agreement with previously reported literature. There are about 0.4 volt per meter per 1 milliamp in humans, and there is about 3.5 times higher high intensity electric field that we see in monkeys, and 50 to 100 times higher electric field that we at this intensity that we see in mouse. So we also know that can also tell us that if, for example, we want to achieve same intensity of stimulation in human as we achieve in monkey, then half of milliamp, intensity of half a milliamp in monkey would be equal to approximately 1.5, 1.7 milliamp in human. We also explored whether because we use different sizes of electrodes, whether the electrode size is relevant here, and at least for small electrodes, we use round electrodes of 3 millimeter in mouse and 50 millimeters in monkeys and 36 millimeter in humans, and then we also put all of them on a human model in order to see if electrode size actually makes critical difference. And the short answer is no. There are some electrode montages where you see less electric fields if you go to bigger electrodes, but at least in this electrode range, so for very small electrodes there is no much difference in between different there is no much difference in induced electric field. So coming back to our animal studies or animal models, as I mentioned, electric field is not the whole part of story. It's also very important to know alignment of electric fields and neurons, because neurons that are perpendicular to the electric field will have will be affected very little by it. Neurons that are parallel to electric field will be affected a lot. Fortunately, we know that in neocortex, neurons are organized very well relative to the surface of the neocortex. They are perpendicular to the surface of neocortex. So we can take a look on tangential and perpendicular components of induced electric fields relative to the brain matter. And again, we see that not only electric field magnitude is very different between mouse and monkey and human, but also distribution of electric field components, both in terms of patterns and in terms of relative presence of tangential to perpendicular components. And in this case, monkeys are actually very comparable to humans, while rodent model exhibit obviously very different patterns of stimulation. To summarize, we see about 50 to 100 times higher intensity of electric field induced in mouse than in humans, and about 3 to 3.5 higher intensity in monkeys than in humans. We also see very large difference in volume of the brain that is affected. So in mouse depend on electrode montage, so you can affect very small volume of the brain if in some electrode montage, but predominantly you stimulate large part of the brain. Obviously in human you stimulate, you can be more focal relative to the brain size. And if you think about tangential perpendicular components and alignment of electric field, mouse maybe not the best model because it demonstrates very different patterns of tangential perpendicular electric field in the brain than monkey and humans. Well, monkey and humans are very comparable, which actually strengthen our animal modeling results, animal results, and demonstrate the utility of non-human primate as a model to research tACS. Coming forward, if we understand how tACS is working in the brain, and we can carefully translate our understanding between animal models and human, now the question comes, what is the best applications in humans and potentially in clinical patients? And here I would like to highlight two recent methods that we proposed. And first of them, the method of applying multiple tACS frequencies and the same location in order to manipulate brain connectivity, known as cross-frequency coupling. So as we know, brain oscillations in the brain, or communication in the brain, reflect informational transfer, and one of the brain connectivity patterns that was postulated to reflect informational processing or to reflect cognitive activity is cross-frequency coupling. Cross-frequency coupling is a dependence between, or statistical dependence between the low frequency oscillations such as theta brain oscillations that are more global in the brain, and high frequency oscillations such as gamma oscillation that are very local in the brain. It was suggested that theta gamma coupling reflects coordination of a local and global brain process in the brain, or reflects processing in some of complex cognitive activities such as working memory. In particular, theta gamma coupling is a part of multiplexing theory of working memory, which says that gamma bursts are encoding individual items, while large-scale theta oscillation provide kind of time coordination for maintaining multiple patterns or multiple individual items in the brain. So such theta gamma coupling was observed not only in hippocampal formation, where it was initially found, but also in neocortex, in particular in prefrontal cortex, and in one of our research that was done in University of Göttingen and in the group of Walter Paulus. We wanted to design a transcranial alternating current stimulation that will be able to manipulate with theta gamma coupling, or in general with cross-frequency coupling, and to explore its causal effects on complex cognitive processes, in particular on working memory. And in order to do so, we design a stimulation where bursts of gamma oscillations were superimposed at the peaks or at the troughs of a continuous theta oscillation. Therefore, we were aiming to provoke bursts of birth of gamma activity or spiking activity at either peak of theta rhythm or either trough of theta rhythm that we also modulated with a slow component. So this was the waveforms, two principal waveforms that we set to explore in our initial experiments. So theta gamma peak with the alignment of a gamma burst at the peak and theta gamma trough. And we used the classical working memory test, which was 2-back, visual spatial, and we use multi-electrode setup in order to apply stimulation towards the left dorsolateral prefrontal cortex, which was previously observed, to demonstrate cross-frequency coupling or demonstrate increase in cross-frequency coupling in such kind of tasks. Then we had 3 sets of experiments. Each column here is 1 set of experiments. In the first experiment, we are in our crossover design. In 1 conditions, in healthy adult humans, we apply sham stimulation in order to have a control behavior. Then we apply classical stimulation tACS at 6 Hz, so it's a single frequency, a simple waveform that modulate continuously theta rhythm, and we saw the improvements, a slight improvement in working memory performance during the application of 6 Hz tACS relative to the control stimulation. But we also applied to our different types of cross-frequency tACS. So the one where we superimpose theta burst at trough of theta and at peaks of theta, and when we superimpose burst at troughs of theta, we saw no effects relative to placebo. So the positive effects of theta alone was diminished or removed by this kind of anti-natural alignment of theta and gamma rhythm. And when we applied tACS with gamma burst at peaks of theta, which we hypothesized would improve theta gamma coupling, we saw a larger increase in working memory performance, which was statistically significantly larger than sham tACS, but also than single frequency 6 Hz tACS. So we demonstrate that there are beneficials, there are additional benefits of manipulating with cross-frequency coupling than just manipulating with a single rhythm, which also demonstrated, provided a new line of causal evidence regarding cross-frequency coupling, but also provided a new interesting method in order to improve cross-frequency coupling potentially in patients that suffer diminished connectivity and diminished cognitive functions. In the second control experiment, we set to explore different frequencies of gamma bursts and how they're related to the effect. And we initially anticipated that high gamma at about 80 Hz would be most effective from the preceding literature, but we also explored different high gamma frequencies, and like at 100, 140, and 200 Hertz, and in general they were effective. They were statistically significantly beneficial for working memory, but the effect size gradually was decreasing because we were moving away from optimal frequency probably. And we had the third control experiment when we explored low frequency gamma bursts on top of theta that show no effect, and when we stimulate only with bursts, so it was either burst with positive offsets or burst with negative offsets, so no theta component, no cross-frequency coupling, no phase to coordinate our gamma bursts, and we saw also no effect. So it's crucially important to have both of these components, theta gamma, if in these methods when you target the cross-frequency tACS. And once again, we can look at the effect side of this. There was no effect on working memory performance during application of gamma burst at troughs of theta or during application of a low frequency gamma burst, but at 80 to 100 Hz we saw significant improvements. At 80 to 100 Hz gamma applied on the peaks of theta, we saw significant improvement of working memory. And we also explored connectivity before and after the stimulation. As I mentioned, rather complicated to explore what's happening in the brain during the stimulation, because stimulation artifacts themselves are very large, but we looked at the connectivity before and after, and we saw significant improvements in neocortical connectivity following those types of stimulation that also demonstrate significant improvement of working memory performance, and no changes in connectivity in other kind of stimulation, despite the fact that they carry exactly the same amount of energy, which also contributed toward our understanding of the role of cross-frequency coupling here. And I want to highlight again another study that was published just last week by Justin Riedel and Flavia Frohlich. He'll look further in cross-frequency tACS, and they explored different types of cross-frequency tACS, not only theta gamma but also delta beta. And in this is a large study, but in one part of that, they looked into two kind of cognitive tasks, one that require little abstraction, cognitive abstraction skills, one that require high abstraction, and both tasks were simple and complicated conditions, so low set size or high set size. And it's known that in low abstraction tasks, that the low abstraction cognitive tasks, they use response tasks, there is increase in delta beta connectivity in neocortex, while in in high abstraction tasks there is increase in delta beta connectivity. In low abstraction tasks there is increase in theta gamma connectivity. So low abstraction tasks like a working memory that I demonstrated previously, and they correspondingly design either delta beta stimulation or theta gamma stimulation. And when assess the effect of stimulation on the tasks, they demonstrate double dissociation. So delta beta stimulation change the parameters of high abstraction task, where delta beta was observed, but not parameters of not behavior of a low abstraction task, while theta gamma stimulation improved behavior in low abstraction tasks, but didn't change in high abstraction tasks, with respect which correspond to the hypothesis, or to what we would expect, knowing how cross-frequency coupling organized in these two different tasks. And they also measured phase amplitude coupling, so connectivity before and after, demonstrate that delta beta connectivity was improved following stimulation, following delta beta tACS and high abstraction tasks, so a task where delta beta was actually involved, and vice versa for theta gamma. So it's a nice demonstration that, of course, theta gamma is not a God's given frequencies, but depending on what task or what cognitive process you aim for, different patterns of cross-frequency tACS can be beneficial. Moving forward, the last topic I would like to touch today is another type of connectivity that we could theoretically that we could exploit using tACS. So cross-frequency coupling is one of the connectivity, is one of the vehicle of information transfer in the brain. Another vehicle of information transfer in the brain is a phase coupling or phase connectivity between different brain areas. So that's hypothesized to be a mechanism of information transfer between brain areas in large-scale networks, such as frontoparietal network, frontotemporal network. And in order to explore whether we can actually stimulate this phase connectivity, we recently had a study in non-invasive, in non-human primates, and two primates with invasive electrodes. We non-invasively apply tACS using just 3 electrodes, one anterior electrode, one posterior electrode, and one return electrode in the temporal area. And they all were on the same frequency, and we manipulate with phase of anterior and posterior electrodes, so with a phase lag between anterior electrode and posterior electrode, and we change all possible phase lags And the idea was to see at which phase difference we would have phase synchronization versus phase desynchronization in anterior to posterior brain area. Coming back to the mechanisms of action, we assume that if there is a phase synchronization, so two brain area exhibit spikes at approximately the same time, then it increases connectivity between these two brain areas because of the Hebbian rule of plasticity. And if spikes in two brain areas happens at a very different time, then that should decrease connectivity between them, and therefore information transfer between them. First, as I mentioned, we explored electric field in the brain while stimulating with tACS at different phase lags. Like zero phase lag of tACS mean that both anterior and posterior electrodes were in phase, and when they're in phase in terms of the current, then in terms of electric field they're in antiphase because current comes from anterior electrode and from posterior electrode. So both electric fields are inwards looking or outwards looking, and there is a gradient change when there is a 180 degrees difference. This is just application of a standard tACS. There is anterior electrode, a posterior electrode, and there are 180 degrees difference between the currents. Then the electric fields are either going anterior to posterior or posterior to anterior. In other words, electric current is always in phase. That is just a standard characterization, but what is interesting is some intermediate condition that we have noticed. So once again, when there is 180 degree difference between the anterior and posterior currents, electric fields goes in like anterior posterior or posterior anterior. And when there is 0 degree, electric fields always inward oriented or outwards oriented relative to the brain surface. But at critical intermediate steps, and for this particular montage, that such critical intermediate step was 45 degrees, we can create an electric field that gradually travels through the brain, and therefore magnitude of electric field so magnitude of electric field gradually travels between the anterior and posterior electrodes, creating a pattern of stimulation that is closely match known types of brain connectivity, and this brain connectivity known as Strolin wave. That's why I call this method of tACS Strolin wave tACS. And again, we can take a look at what happens in the surface. So previous data were recordings. This is a simulation. This computer simulation at 180 degree difference between anterior posterior electrodes, and at 0 degrees when the electric field is just experience peaks and troughs, so it's coming up and down. And when we have intermediate or Strolin wave tACS, again it's just 3 electrodes, 1 anterior, 1 posterior, and 1 temporal. We can create a phase shift that will force electric field to gradually move through the brain, and therefore first provoke, in this particular example, let's say provoke spikes in more posterior areas, then gradually in more anterior areas, which closely remind a real life phenomenon of in the brain known as Strolin wave, or patterns of the brain connectivity known as Strolin wave. And we looked at the agreement of our E-field modeling. Here on the top there is E-field modeling that we did, and an experimental data, and found very high agreement. So you can really use computational modeling in order to predict such type of stimulation, and I would actually encourage use of computational modeling here because there are way too many parameters here, so you need to know phases of different electrodes, and you need to know their arrangement. In other words, this is a 4-dimensional stimulation. There are 3 space dimension and 1 time dimension, because in this case you actually use time domain. You create a stimulation that behaves differently in different space and different time. Anyway, in using relatively simple and readily available hardware setup with just 3 electrodes, you can create a Trailing wave tACS, and we are very positive knowing the mechanism of tACS that will allow you to manipulate with trailing waves, and hopefully very soon I will be able to report on first results in using these techniques in humans. On that, I would like to finish the lecture part of today's webinar. I hope I convinced you that tACS is a reasonable method to manipulate with neural spike timing, and therefore with brain connectivity, so with spike timing in different brain areas, and it has very intriguing applications in humans, and there are a lot of things that still we are set to discover in the future, and to bring these methods towards robust application in clinical practice and in patients. Thank you for your attention, Rafał.
Thanks, Ivan, for the excellent presentation. So we are ready to start Q&A. We are waiting for some questions. So actually, before we get to the question from audience, let me highlight some points and actually ask some questions. So let's start from the end regarding the traveling waves. Mm-hmm. So I guess that there is a way actually to calculate the speed of the traveling wave.
Mm-hmm. Yes.
And somehow tune the tACS, artificial traveling wave, to the natural occurring waves, because this is the goal.
Right. Yes. So in this method, speed of traveling wave would be a direct function of frequency of tACS, and as one parameter, and electrode location or relative distance between them as another. And I would say naturally you would look at traveling wave in large scale networks somewhere between 1 to 10 meters per second, somewhere in this regard. And it's actually what we got with 10 Hz stimulation. So you can optimize to have this relatively slow speed moving electric field. Here, by the way, there is a little bit of confusion, because people who know physics know that there is a concept of trailing wave there, which relate to propagation of electromagnetic waves. And it's also called trailing wave there, and they are propagating with the speed of light, pretty much, which is much faster than 1 meter per second. But in biology, there is a different phenomenon that's called trailing wave, right? It's just observation of if you record electric fields from the brain, or if you record local field potential from the brain, from different brain areas, you see that there is a types of phase synchronization, right? When there is a peak of local field potential in one area, then in next time point there are peak in next area, and the next time point there are peak in third area, and so on. So trailing wave here is more like epiphenological. So it just brain areas that gradually communicate with each other.
Okay.
And you can create like with tACS, you can create electric field that is moving as slow as you want. It's a direct function of the frequency. So
okay, okay, thank you. However, I guess that what we are presenting is across the stick, the depth electrode. And if you take into account the folding and the cortex, that will be quite harder to predict.
Go back. Absolutely.
You did the modeling.
Absolutely. Okay. You're absolutely right. When we look at the surface, that is, of course, would be slightly more complicated picture. So we did computational modeling in order to see how it looks at the neocortex. It looks reasonable, I would say. So then Obviously, in the sulci, in the folding of the brain, there will be less of electric field will be weaker, but the general pattern of, let's say, having peak of electric field that is moving through the space, this general pattern holds. So I would say it would very much depend on a particular application.
Okay, perfect. Thank you very much. So let me only quickly highlight, I think, the most important point from your presentation regarding the experimental research with intracranial electrodes that we can obviously not find easily, conducted in humans and in non-human primates, in monkeys, which is actually the best model of translational brain stimulation. In awake animals, I think this is quite important to mention here, because you know that we know that anesthesia somehow can modify the excitability of neurons, increase the threshold, and I think the most important, the findings related to the application of a relation, the proportional interaction of current intensities and the increase in the percentage of neurons entrained by tACS with the electrical field. And in awake primates. So it's clearly the dose-dependent impact. So actually here comes the question, so what would be the next step with the development of novel methodologies allowing to safe application of higher currents? It's what I understand, it's what we need, higher current intensity, and getting large effects actually on neuronal entrainment. We hope you know that we have a neuroelectrics actually multi-channel system that we can go up to 4 milliamperes total current. But so should we go more, or what would be the solution in this direction?
I think move towards high intensities is one of them, maybe not much more than 4 milliamps overall per brain, but maybe slightly more eventually will be used. And I think with multiple electrodes and with distribution of this current, like through multiple electrodes, it actually getting more tolerable. But I think the 4 milliamp dose, like in humans, that is plus minus 4 milliamperes per instance. That is really really sufficient, because you would get somewhere around 0.4 volt per meter in electric field in humans per 1 milliamp up to. So I would say the goal would be to go closer to like 0.5 to 1 volt per meter in the brain in a human. That's probably would be the more effective range than where we are here, and 4 milliamp would be fine. But I would say more control, more understanding of what's happening. So more control over current per electrode, application of multi-electrodes, not only in terms of 4 times 1, not only Laplacian montage, but more complicated montages, high involvement of modeling, high involvement of neuroimaging. It's all eventually will bring us that towards more effective applications. But okay. Higher doses is something,
that we should
intuitively higher dose should do better.
Yeah, especially when you presented the results comparing the rodent monkeys and humans, we can see that we should go actually to higher current than in this case. So let's go to the Q&A we have from our audience. So first question from Rob. So this will be related to the beginning of your presentation. Would different brain regions respond to different tACS oscillation frequencies? Is this one-to-one related to brain oscillations, in example, delta, theta, alpha?
It is closely related to brain oscillations, and I think, well, the answer for sure, yes. Different brain regions would respond to different tACS frequencies. I would go even further. I would say that this is a multi-dimensional problem. So there are brain regions, there are brain states. So whether it's rest, whether it's a certain type of activity, motor activity, cognitive activity, And I'm very positive that depending on where you stimulate and depending on when you stimulate, different frequencies or same frequency will have different effects, or different frequency will have different effects. And I think it was even shown, like the most classical tACS work would be application of alpha stimulation to occipital cortex, which has different effects than application of alpha oscillation to prefrontal cortex, let's say. So yes, for sure.
Okay. Next question from Maya. Can we please get some clarification on the difference between spike timing and spike rate measures? So this is related to the mechanism of the effect of.
Thank you for the question, Haya. And spike rate is a total amount of spike per time, per minute, let's say. So how many spikes overall? Spike timing, or when I reference to spike timing, I meant phase entrainment. So sorry if it wasn't, if I didn't clarify it initially. That is relationships of a spike to the phase of applied alternating current. So whether spikes come, let's say, at peak, at fallen phase, at the trough, and so on. So if there is no change in the spike rate, it means that per minute, let's say this neuron generated, I don't know, 100 spikes. But these 100 spikes can be distributed randomly, or they can come in bursts. So let's say 10 bursts of 10 spikes. Or they can cluster. Let's say more spikes will occur at peaks of tACS waveform, and less spikes will occur at troughs of tACS waveform. So although the overall amount of spikes hasn't changed, the patterns of spiking did change. And it's a class, at least the fundamental theory of neuroscience to date tell us that patterns of spiking is also one of the encoding mechanisms. So of course spike rate is an important mechanism of informational signaling in the brain, but patterns of spikes, whether they come in bursts and so on, it's also one of the mechanisms of communications, even at the level of individual synapse. But also, obviously, because we stimulate large brain networks, and if we stimulate, let's say, prefrontal brain network, and all neurons there now preferentially spikes at the same time and don't spike at the same time, then this is increased connectivity within this local network, because that's how every mechanism of plasticity works. Neurons that spike together, wired together.
Okay.
I hope that clarified.
Yeah. And actually, following with this, I have seen that actually with the higher frequency, 70% of the spikes were not detected actually, based on TAC during the tACS stimulation. So would be which method actually would be the best to actually monitor the effect of tACS? I guess the EEG wouldn't be the best, because we cannot see effect of the macro scale. You are getting only 30%, no? Even with the maximum what we watch was 1.5, and not everyone has access to the intracranial recordings.
That is complicated question. I think at some point you would need to get creative. There is a development of fMRI tACS. This research that's going in many places in the world, and it seems that tACS has effects that are visible on fMRI, and these effects are different from just artifacts of flowing electric current. So you can consider maybe fMRI application. That is not the cheapest way to look at that, but it may be more accessible than invasive recordings. Depending on your paradigm, maybe eye tracking can give you some information, although not so much research about that, but I have an internal feeling that may be a way to go in some cases. But EEG, MAG, it was demonstrated that in some conditions, using some advanced method, you seem to be able to recover some information. But like overall, of course, if you stimulate with electric current and you record electric current, that's hard to do. Maybe you should go for pre-post measurements. So we're working with what we have, but there is definitely chance to use different modality of neuroimaging. So fMRI, maybe eye tracking, some cognitive tasks with cognitive modeling in order to dissect exact parameters of behavior also is a promising approach.
Okay, thank you. So we are going with the question from our audience. Next question from Cyril. I think this was directly related to the paper from Krause 2019, where we were talking about mechanism. Could these measures be related to the distance between the tACS electrodes, in addition to the intensity of stimulation? What could you have obtained with a smaller between electrode distance over a specific structure, like M1, for example? And second, could this be related to the nature of neurons stimulated, different effects for different neurons?
For the second questions, I am absolutely sure that this is the case. Different neurons would have different effects, and I would say, in my understanding, it's actually, there are two questions here. First, there are physiology of neurons, right? There's different, like inhibitory, excitatory, all sort of types. There are dozens of types, and they exhibit, interneurons have very different behavior from pyramidal and so on. And second, even their physical arrangement. So pyramidal neurons are very elongated, very large. If they are along the electric field, they capture a lot of effect, right? If you have a small circular shaped neuron, then of course it has hard time to capture electric field. So it's physiology and physics of neuron both will drive that. Regarding the first sub-question, could it be related to distance? Distance between the electrodes per se doesn't really important. It only creates electric field. So distance is important to a degree to which it creates different electric fields. Obviously, the shorter the between electrode distance, the weaker will be electric field, but more focal. That is a rule of thumb. There are different options, but in general, that's the rule of thumb. The closer the electrode, the weaker the electric field, but more focal. And then it goes towards what brain process you're modulating, whether your brain process is really focal, whether you need to go strong, to go slightly deeper in neocortex, and so on. So distance is only relevant to a degree to which it changes the electric field in the brain.
Okay. Thank you very much. Next question from Lindsay. Actually, we are jumping to the cross-frequency stimulation part. Does the timing of the cross-frequency tACS affect the improvement of behavioral results in working memory task? Say, if the coupling waves delivered through the cross-frequency tACS at exactly the same time as the working memory task begin, does it work better than if it's delayed?
Good question. The most honest answer is I don't know. However, I can speculate. It probably affect, but probably like the better you align to an intrinsic brain process, the larger effect you will get, hopefully, or at least more robust effect. So more consistently effect, more reproducible effect. But there is a lot of things here interplay. In interplay. It's like it's hard to apply such simulation in kind of closed loop when you read stimulation and write it, because you cannot do it at the same time. So you need to predict. Then you also need to keep in mind that the tACS itself have timing, right? So it takes time to apply such modulation. And the most important, unlike TMS, tACS doesn't provoke spike and only modulate neuronal activity. So if it's not there, it doesn't modulate it. If it's there, it does, in my understanding. So the timing here is not that critical. We apply the stimulation, and whenever this connectivity processes emerges, or we can modulate that. So that's how I think about that. And if there is none, if there is no intrinsic cross-frequency coupling in this brain area, it has no value, then probably you will not change anything with the stimulation. So you will not force what is not there. That's why timing is not necessary, is not as critical as for, let's say, TMS. But I also don't know, because I didn't apply cross-frequency coupling tACS in a closed-loop fashion or something. Okay. So that would be interesting research.
This is something to come. We are waiting.
Yes.
Next question from Hamdi. Thank you for a great talk. How long do you think are the tACS artifacts at commonly used intensities, 1 milliampere in humans? I think how large probably, no, was the question.
Sorry, can you repeat the question again?
It's the one from Hamdi. How large do you think are the tACS artifacts at commonly used intensities?
Oh, yeah. Depending on what is your recording modality. If you record EEG, well, they probably 1 million larger than your signal. If you record single units, they are, in raw data, they are somewhat larger than the spikes, but at least in the same order of, you can easily filter them out. Yeah, depends on modality. Yeah. But for EEG and MAG, they are dominant. They're pretty much the only thing you see.
Okay, thank you. Next question, actually, I think you answered this already. When you create the phase gradient, do you need to know the biological traveling wave speed and try to match it or them?
Ideally, yes, that would be a way to go.
Okay, thank you. Next one from Morteza. Thank you for a nice presentation. Would you please elaborate on single hertz AC stimulation versus range AC stimulation and the differences in mechanism of action and efficacy?
Okay. Depends on the range, because I mean, this process happens in time. So if you would create a tACS waveform that it's instead of, let's say, 10 hertz would be like between, I don't know, 8 and 13 hertz, right? So you in principle can do that. Waveform that's slightly going faster or slower, but you should keep in mind that like it will take a long time to accumulate this randomness, right? At every given point of time, you stimulate like with something, or I would put other way around. If you create such a waveform that goes slower or faster, then at any given period, at any given second, it still goes like at around same frequency, right? Because that's how you define frequency, like amount of periods per second. So if you want to make sure that you stimulate with tACS, because I heard about these ideas, let's say at around 8 to 13 hertz, it will take you like 20 minutes long stimulation to accumulate, to actually create something random enough that by the end, when you calculate FFT of this waveform, it actually spans the range. But if you think about high range, like 1 to 640 hertz, then it's called transcranial random noise stimulation or something. That's possible. But in terms of mechanisms, if you have a narrow range, it's exactly the same mechanism. At a peak of your oscillation, there will be increase of spiking. At a trough, there will be decrease in spiking. I don't see much difference here.
Okay, thank you very much. Next question from Aya. Thank you, Ivan, for such a comprehensive and informative talk. Is there any evidence of tACS induced changes in neuron excitability, increasing, decreasing likelihood of firing, perhaps in conjunction with spike timing changes, or are these two separate mechanisms?
I think this mechanism at least partially separate. Likelihood of firing, I think in non-human primates or in at least in alive animals, there is no solid data on that. I'm looking, so I demonstrate that there are some evidence that there may be change in burstiness that of spiking during tACS that is possibly related to excitability. But that is something that we observed in our data, and we will explore this in the future. But so far, I would say that excitability remain a domain of tDCS. And if you're looking into neural excitability, I would try to look in direct current literature, because they have much more clear line of evidence and mechanisms of that.
Okay, so maybe that's why came the question, because on tDCS we have clear evidence, and we are just moving the field a little bit to tACS, or exploring the field of tACS. Okay, next question from Ivan regarding what do you think about complexity modulated tACS scenarios? So I don't know what you mean complexity, but you are using always a complex pattern for the stimulation.
Yeah, I'm not sure what's meant here. Is it complexity like entropy of signal, or complexity modulated tACS scenarios? Please clarify in questions what do you mean by complexity?
Regarding the next question from Mortesa, is the request for the updated information regarding current literature and interferential frequency stimulation. So actually, we can also redirect here our audience to the literature, and where you can find information regarding the cross frequency or interference temporal wave stimulation.
Yeah, I mean, inferential currents is another approach that is recently reemerged in tACS world. I think it still remains to be fully demonstrated in large animals or in humans how deep is actual inferential current can go. However, in rodents it was at high stimulation intensities it was working. I'm not the best person to ask about inferential currents because I'm not using them themselves. But this is something that is hot, and take a look on the papers of Neil Grossman probably.
Yeah, we can also redirect to our webpage neuroelectrics.com. You can find information regarding different techniques, and including also temporal waves. Next question from Shuka. Is there any possibility that when measuring electrodes are implanted in the animal and tACS is performed, spikes are obtained as a result of the electric field being concentrated on the measuring electrodes?
Probably no. That's not the case. So this is one of the concerns we had, where the electric current is actually leaking through the electrode, through the measurement electrode themselves into the brain. And I think that's not happening. And I think that because we measured electric field in the area using the same electrodes, and if electric current would leak through the electrodes, then the electric field would be, when we measure, would be really chaotic, or would be inwards outwards to relative electrodes. But our electric field is very well organized. It goes along the axis that connected to two stimulation electrodes. So we have left and right stimulation electrodes, and all electric fields is along this left-right axis. And we measure that in the recording area using the same electrodes. So I think most of the current follows the path it would follow in a normal brain without invasive electrodes. Otherwise, we would see a lot of leakage through the cranium, so there will be a lot of inwards oriented currents, so go from top to bottom, or like a lot of spirals around of electric field around the recording electrode. So there would be way more chaos in that. And the fact that we see well-organized electric field tells me that probably most of the current goes as expected and doesn't leak through the recording system.
Okay, thank you very much. We would like to finish all questions actually, so we have to go a little bit faster. Question from Andres: how can you relate the neurophysiological mechanism of working memory with cross-frequency coupling?
That is not the question if you want to go faster. This is a great question, but really long one. In very brief words, neurophysiological mechanism, if you agree with multiplexing theory of working memory, so there are slow oscillation that provides organizational structure to the working memory, and then there are fast oscillation that process items along this organizational structure. Then this is the mechanism that is reminding cross-frequency coupling. There are large-scale slow theta oscillation, and then there are bursts of gamma, and the bursts of at different periods of theta. And this burst of gamma would encode individual items, and the theta of itself will provide organizational structure to maintain different items in different shelves.
Okay, thank you. Next question from Guillermo. Did the cross-frequency tACS has an increase in the firing rate after the stimulation, or did the entrained cells we see during the tACS stimulation continue after cross-frequency?
I hope to answer on this question very soon, because it's really interests me, but for that we need to do cross-frequency tACS and invasive research. I'm all right.
You didn't measure this, yes, actually,
no,
yeah, because there was a different presentation with invasive electrodes, and then the presentation with the tACS, but this was with standard EEG. Okay, yes. Question from Banya. Thanks for the nice talks. Do you think tACS could have a place in neurorehabilitation in the future? In particular, could you help in patients with stroke, traumatic brain injury, or the brainstem injury?
I really hope so, and I know that a lot of great scientists are working in neurorehabilitation and trying to use tACS with a considerable success. And I think in case of stroke, there may be even phase 1 clinical trials going. Okay, question from John, actually related to our previous webinar, research in advancing supporting the use of gamma tACS for clearing amyloid in Alzheimer. Target areas and electrode placement seems to be an open question. Do you have any insights? I think speaker of your previous seminar,
yes,
which is probably Emiliano Santoneci, would be the best person to answer. So if I don't have insights over what he could tell about that. Okay. So actually we can redirect our audience also to our webpage, where you can find our previous webinars and find information. So this was actually our last questions. Would you like to add something, Ivan, comment? I think, thank you for inviting me for this webinar. It was a great pleasure to talk and to see that so many people are interested. And I think that I'm really happy to see how many cool developments are happening in the tACS field in the recent years. So I highlighted some studies of our colleagues. Obviously, there are many more. And I hope in the future years we will have even more exciting information, both from me and from my colleagues. Okay. Thank you very much. Thank you for the presentation, for your answers. Thank you all for questions. And I want to thank everybody for joining us today. I hope you will join us again for the next webinars. Please remember to visit our webpage, neuroelectrics.com, for the information regarding upcoming webinars. Once again, thank you very much. Stay safe, have a great day, and we'll see you next time. Take care and goodbye.